Okay, I get it. I'm sorry. I threw a banana peel at you for suggesting space telescopes as a solution to the Starlink versus astronomy problem. And I get it. Space telescopes are a really good solution for a lot of astronomical issues, like the fact that there's an atmosphere in between observing sites and the stars. But are space telescopes truly a solution to the Starlink problem? And how bad are satellite streaks really to astronomers? Can't they just remove them with software? If you have no idea what I'm talking about, by the way, go check out my previous video called Is This the End of Astronomy? In this video, I'm going to go into depth about some of these things because honestly, I wondered the same things. And in the research process, I found that the answers aren't as simple as you might think at first. So without further ado, here's Johnny from the past explaining how bad are satellite streaks really. This is what 42,000 Starlink satellites will actually look like. Not to the human eye, not to a backyard telescope, but to a camera or a mega telescope, taking 30-second exposures every frame. And this isn't an animation. This is a photometric simulation. Don't astronomers and astrophotographers always take multiple exposures, one after another, and like, oh, that last one had a satellite streak, let's just toss that one. Like, why don't you just do that? Or also, like Photoshop can do content-aware fill and remove things that you don't want in the image. And I was genuinely curious about this because when I talked to Tim was very skeptical that this is a problem at all.
Let me go on the record saying I am far from an expert. I know nothing about astronomy. I am not an astronomer. I am not an astrophysicist. So this does not affect my daily life. It does not affect my daily work. So I am absolutely pre-apologizing if I am entirely ignorant of some of the processes here. And I would gladly be corrected. And I hope that I learned something if there is a glaring problem with something like this. I can speak from the astrophotography world because I've done my fair share of astrophotography as a professional photographer for, a decade. But I see it as, okay, like for the optical things, the thing that people are reacting to a lot is these pictures that we'll see where, someone's taking a photo like of Neowise, the comet, or, taking a picture of something, they just see it ruined by all these streaks. Those pictures will be everywhere. We just see, those just get regurgitated constantly. It's like, this is what Starlink is. This is Starlink. Do you want this? And that's the feeling that we're all getting given to us. First off, there's obviously conditions. You can't really see satellites in the actual middle of the night. You're in the shade. You're in the shadow of the sun. They're in the shadow of the sun. You're not going to see them. There's already, how many times do you go out in the night sky and ever see a satellite? You're way more likely to see a plane. Like 99% of the pictures I've ever had ruined by anything is by a plane. Like, planes exist, okay? And no one's saying, like, get those planes out of the sky. They're ruining the night sky. Like, and the satellites are really only visible for, about 90 minutes after dusk, 90 minutes before dawn, generally, right?
Initially, I thought that was true as well, and I couldn't quite understand why astronomers still thought it was a big deal. Like, what's all the hype about if it's only, the 90 minutes before sunrise or after sunset? But it turns out that it's not just 90 minutes. Like, in particular, for the half of the year surrounding the summer, the nights are much shorter than they are in winter. So, what that means is the satellites are going to be visible for longer because the Earth is still tilted in the direction of the sun and they're still illuminated up there. This only became clear to me after writing that photometric simulation I was talking about earlier and testing at different latitudes, different places around the Earth at different seasons. What does the impact look like? And those streaks are visible for like half of the year in half of the sky. But even in the summer, what do you do if you, take a picture or take a picture with your mega telescope and a satellite streaks straight through it? Tim had a perspective on this from the astrophotography world.
Those photographs, by the way, when you see a streak and all these things, that's called like a positive stack. Like you can positive stack the included or like new pixels, or you can do the opposite of that. When you're in Photoshop, you can do a negative stack where you're removing so you could literally just like click a button in Photoshop and it would be gone.
Okay, if that's the case for astrophotographers, what about astronomers? Like people actually doing astrophysics research? Like, Is this even a big deal if software can just take care of it? So Meredith actually writes the algorithms that remove satellite streaks from images. And she explained how big a deal these streaks are going to be in her work.
If there's streaks in an image, it is computationally straightforward mostly to detect where those streaks are and to do some kind of image subtraction or masking or removal or whatever you want to call it. There's different subtleties. Now, just because it's doable doesn't mean it doesn't take actual person hours to do. And you're also not going to necessarily do it perfectly. So there's some subtleties there. But where you really get into the issue is just the sheer number of these things. So for example, one science case is for something called weak lensing, which is not my area of specialty, just disclaimer. But the idea is that you can learn about distribution of matter in the universe as a whole by kind of looking at small overdensities here and there, like in every different direction.
Light from distant galaxies doesn't move in a straight line to our eyes. Because of the gravity of all the things in the universe in between us and that distant galaxy, the light gets distorted in a lens-like way. And usually it's somewhat weak of a distortion. But by precisely analyzing the way that these galaxies are distributed, there's a hope that we'll uncover clues to the decades-old mystery of dark matter, the mysterious stuff that makes up 85% of the universe. But Starlink and the other internet constellations are set to make this kind of observation impossible from the ground.
If there's a whole bunch of crisscross subtracted thingies, like, your noise is wrong. You can't do your science. Like, you literally cannot. Like, yeah, sure, you can make a pretty picture image for a calendar, or I could study star variability, or I could study, I could use it for lots of science, but not for those sciences. And that is one of the main, well, there are many main science drivers, but that is one main science goal of Urban Observatory's LSST, is to be able to do that kind of science where you really need highly precise background noise measurements. So the other example that comes to mind is a lot of solar system science. So, not all solar system science, but some you have to actually look kind of towards the sun, because that's like how orbits work and where the stuff is. And that's, of course, where the most brightest satellites are, because they were bright, because they reflect sunlight. And in twilight, like shortly after sunset and shortly before sunrise, that's when the most satellites are going to be bright and visible. And so if you're trying to find, like, for example, killer asteroids, which is like an actual science driver that we actually will do with Rubin, you're not going to be able to find them if it's just a bunch of satellites. So I think the ultimate irony would be we couldn't find the killer asteroid because there were too many low Earth orbit satellites. Right. Sorry, everybody.
So this is one of the sciences that satellite constellations are going to make impossible. But it's not the only one. If you're taking pictures, you can remove the streaks one by one. When we're talking about 42,000 satellites, that's not going to be so simple, because every single picture is going to include a satellite streak. But if you're taking spectra, like what Dr. Becky does, you don't have the ability to remove a streak.
Yeah, so I research how galaxies and the supermassive black holes that live in the middle of them evolve and change together. The stuff that's being taken in and the black hole is using to grow is hydrogen gas, right? It's the most abundant thing in the entire universe, right? So you can imagine sort of the hydrogen gas is spiraling around the black hole. Now, hydrogen gas that's excited, shall we say, so it's had radiation put on it, maybe from stars that are forming around it, emits light at a very specific wavelength. And that's because in hydrogen, if you remember sort of chemistry 101 from school, we have a proton in the middle and an electron orbiting around the outside, right? And that electron can, if it's excited, if light is shone on it, it can jump up to the next energy level. But it's not supposed to be there. That's not what hydrogen is supposed to be like. Hydrogen in its base form is that sort of proton, and then the electron as close as it can be to the atom. So it drops back down. But quantum physics tells us that those energy levels around atoms are always separated by the same exact amount of energy. And so as the electron drops down, it loses that amount of energy in the form of light. Now, because it's always the same energy, it's always the same color or wavelength of light that's emitted. And so if you were to sort of plot that on a graph, it's sort of like, here's all the wavelengths of light we're detecting. It would be one big spike at the wavelength that you'd expect hydrogen to give off. And so we see that all around the universe. And it's a great tool for figuring out, like, you know, how do galaxies rotate and like how much hydrogen is in this area. But it's also a great tool for measuring the mass of the black hole, because if you've got hydrogen spiraling around the black hole, you've got some of it coming towards you and some of it coming away from you. So you don't get a sharp spike. It's sort of blurred out and broadened to look like this, because some of it's coming towards you, some of it's coming away from you in like a Doppler shift, or we call it a red shift or a blue shift as well. And so if you measure how broad it is, you know how fast the hydrogen is moving. And if you know how fast the hydrogen is moving, you know how big the thing is that it's moving around. And so all you need to do is go to a telescope, which is what I did during my PhD. I went to a telescope called the Isaac Newton Telescope in La Palma. It's great. You're above the clouds on top of the mountain, and it's just the most eerie and incredible view. And we took spectra of galaxies, which is where you take the light and you split it through a prism to get sort of the component wavelengths. You know, you get its rainbow, and you can record how much of every wavelength or color you receive on the detector. And so therefore you can record this nice graph of the broadened hydrogen emission line. And then you can go, all right, let's measure that. Okay, so this black hole is 4 million times the mass of the sun. Cool.
Now, because you're not taking a picture of a galaxy, you're taking a spectra, you're taking that galaxy's rainbow, you don't have the ability to remove that satellite streak at all.
These satellites are very close and they're very bright, reflecting the light of the sun. So as soon as one of those passes over, you know, you've just got a spectra of the sun. Basically, you've just completely lost all the signature of the galaxy. You know, images that I take are of galaxies that are very faint. And so I have to observe sometimes for 6 hours total on one single object. We have to split that up into maybe sort of like 20-minute or 30-minute chunks, right? Just so that if something like a satellite does streak across your observation, then you can always remove that exposure, and you don't have to use that little 20-minute chunk, right? You can use all the rest of them, and it should be fine. But you have to balance that with the fact that reading out the detector takes a long time, and so you don't want to add that, like, what we call overhead of like readout time to your observing night, because it like wastes time that you could be observing the sky. So it's a bit of a trade-off. But if you've got a big constellation of satellites tracking across your image, that's more of your data that you've essentially got to throw away.
These are just the tip of the iceberg. This is just the kind of science that Becky and Meredith are talking about. There's a whole bunch of other ways of looking at the universe which are going to be impacted. And by this point, it might be obvious to you of like, we've got to start putting up space telescopes, and fast, especially because, you know, Starlink and OneWeb and Amazon's constellation and Facebook's and Russia's possibly and China's possibly, they don't need to be magnitude 8. They don't need to be magnitude 7. They don't have to abide by these astronomical guidelines at all. And Starlink in particular shows no signs of slowing down. They're launching as fast as they possibly can. So how much would it really cost to transition all of astronomy into space? And is that even something that's reasonable? Well, it took me a little bit of time to find out, which is why I'm filming this on a different day about 2 weeks later from that previous clip. But here's what I found. And in order to understand this number, we're going to have to dive into telescopes and how they work a little bit. All telescopes are essentially light buckets. Light comes from distant sources, stars and galaxies out in space, and then it enters some device which focuses those light beams. Back in Galileo's day, these pieces of light were shaped into focus by using pieces of glass that were very carefully constructed. These are refracting telescopes because they refract the light into focus, kind of like a camera lens. But you can only bend light so much without losing a lot of that light in the glass itself, dimming the source that you're trying to look at. And so nowadays, it's much more common to use a mirror, a curved mirror, usually parabolic or hyperbolic mirror, which bends that light into a focal point. It's kind of similar to glass, but in this case, it's just shiny. Obviously, it's a mirror. The larger the mirror, the more light you can bend into focus. And so you can see dimmer and dimmer objects, or take shorter exposures if you're hooking a camera up to it. These are called reflecting telescopes. But not all telescopes take in the same color of light. Light comes in many colors, most of which are invisible to us, but which the universe is full of. These colors of light that we can't see are shown here on the electromagnetic spectrum. That tiny little window is the colors of light we can see, and the rest is the colors we can't. Optical telescopes like this one take in the colors that humans can see. But there's other telescopes like radio telescopes, which look at things in the radio frequencies or microwave frequencies. And even some space telescopes, which can look in the ultraviolet, like Hubble, for instance. So here's a question. Why do radio telescopes have to be so huge? Why does nobody build like baby radio telescopes in their backyard? Well, it comes down to the way that light waves work. Different colors of light have different wavelengths, meaning how large are these waves, literally, like in meters and physical scale. The length of a single wavelength of green light, for example, is about 500 nanometers. That's about the width of 5 human hairs stacked right next to each other. So it's kind of hard to... So that's a really small wavelength, but infrared light is about 1 millimeter. So one wavelength of infrared is about a millimeter. And the VHF, or very high frequency radio wavelengths, like the ones that ATC uses to talk to pilots and aircraft, those waves are about 10 meters across. And so on and so forth. There are some really big wavelengths out there. And so, to look out into deep space, you need to have a reflector in your telescope that's at least as large as one wavelength, and ideally much, much larger than that, so you can actually have some resolution in your detector. If you think about our eyes have a pretty small entrance pupil, but that's because visible light can fit in there, enough of it, so that you can actually have some resolution to see colors in your surroundings. If we had tiny entrance pupils, we wouldn't be able to see with the same resolution. There's also a consideration of what happens to the light as it passes into the barrel of the telescope. If the barrel of the telescope is too small, when the light comes in, it'll bounce off the edges. It'll diffract. This makes it impossible to see the light that's actually coming in, because now it's bouncing all over the place and spread out. This limit of what wavelength of light you can actually resolve with your telescope because of its entrance aperture is called the diffraction limit of a telescope's aperture. Okay, so knowing all of that, how can we estimate how much it would cost to move all of ground-based astronomy into space? NASA's Marshall Space Flight Center in 2018 released a report which gave a cost model for space and ground telescopes. It's been refined over the course of 20 years and fit to a 92% certainty on a database of 47 telescopes. Those are both ground and space telescopes. And the equation is actually pretty simple. For a space telescope, you first take $20 million times the aperture diameter of the telescope to the power of 1.7. So the larger the diameter, the more the telescope's going to cost, obviously. Times its diffraction limit wavelength to the power of negative 0.5. So the shorter the wavelength, the more it'll cost. Times the telescope's operating temperature to the power of negative 0.25. The colder the temperature, the more the cost. Times a year of development factor, which is e to the negative 0.028 times y minus 1960. Y is the year of development of the telescope. So I guess in our case, at least 2021. And then times 30 if it's a space telescope, or times 1 if it's a ground telescope, because space telescopes generally are about 30 times more expensive than ground telescopes. This model is the best model for estimating the cost of a space telescope that I've been able to find. And even so, its certainty is only about plus or minus 50%. But let's run with it anyways. There are thousands of optical observatories around the world, but let's just consider the top 40 largest. If you were to put the top 40 largest telescopes into space, just those, how much would it cost? Well, plugging in conservative parameters for all those things we just talked about, we land at a number of about 49.909 billion US dollars. That's a lot of money. Now, just to be conservative, let's assume that this is overestimating by 50%. So that gives us a number of $24.955 billion. That's still a lot of money. To put that into context, Elon Musk estimated in 2016 that the total cost leading up to the first Mars launch that SpaceX would be able to do would be about $10 billion. NASA's entire 2020 budget was $22.6 billion, with which they employed over 17,000 people, continued doing science with flagship climate orbiters, launched American astronauts to the ISS, supported the ISS, kept ISS running from mission control in Houston, launched and landed a rover on Mars, and the list goes on and on. If all that effort was suddenly redirected to putting all of ground-based astronomy into space, it still wouldn't be enough money, at least for 1 year of NASA's budget. And by the way, this does not include launch costs at all. So you'd have to add launch costs on top of these telescope costs. So why are space telescopes so expensive, and is there any way that we can make them cheaper? Well, space telescopes face space issues, and this is one of the biggest reasons why they're so expensive. Space issues include things like operating in the vacuum of space, where the temperature on one side of your spacecraft is hundreds of degrees higher than the temperature on the other side. You have to deal with solar radiation, flipping bits in your flight computer and potentially causing a bunch of chaos. And because there's no AC outlets up there in space, you have to find a way to make enough power to actually support the telescope that you're building. And not just the telescope, but also the control systems like the reaction wheels that are pointing your space telescope all over the place. And not just that, but you also have to face the fact that things break. And what do you do when a part on your telescope actually fails? Currently, we don't really have a way to go up and fix things in space. We might in a couple of years, absolutely. I'm not saying it's not possible. I'm just saying that these are the challenges that we have to face in order to bring the cost of space telescopes down tremendously. As it stands, there are only a handful of groups around the world that build hardware for space. And even then, it's usually a one-off. Maybe if we started to build space technology at a high rate, we could bring the cost of some of these subsystems down. Maybe there could be a standard electronics and power generation bus with a solar panel attached, rather than building a brand new, fresh, bespoke solar panel for every new satellite that gets launched. But some of the other challenges like power generation and keeping the mass of things down to a minimum, that could take a really long time to conquer. For instance, the ground-based Vera Rubin Observatory will use 6 times more power than the entire International Space Station solar arrays can provide. And those things are literally the size of a football field. The Vera Rubin Observatory is also heavier than any launch vehicle in the world can actually lift right now. It's just above 65 metric tons. And that's just including its camera and its mirrors and some of the computer hardware that it's going to have. That doesn't even include any structure or the reaction wheels that you would need to point this thing at different targets. So these are some of the reasons why space telescopes are so expensive. And until we can conquer some of these challenges, I think it's unlikely that we'll be able to launch tons and tons of space telescopes to replace ground telescopes, which can't really operate as well because of Starlink. So one idea that Tim actually had in the previous video, and then some of your comments also in the previous video suggested, is why don't we just tack a bunch of, small telescopes like this one, or maybe some reflectors on the side of Starlink satellites? Wouldn't that solve the problem? If you could have a huge web of telescopes all working together. Well, just like we were talking about earlier, the bigger the mirror, the bigger the light bucket on a telescope, the better. Hubble's mirror, for example, was only about 2.4 meters across. That's pretty small compared to the 8 meters that we can create on Earth for ground-based telescopes. And because of this, it's pretty commonplace for Hubble to spend a very, very long period of time looking at the same object, adding up light night after night. If it had a bigger mirror, it could probably shorten exposure times, making it more useful to more scientists and astrophysicists around the world.
I think what you have to get across is how oversubscribed not just space telescopes are, but ground telescopes are as well. Some of the more popular ones, it's, a 1 in 10 chance of your proposal for, I want to look at this thing with this much time on the telescope to get accepted, right? For things like Hubble, which is supposed to be retired, it's even higher than that. It's like 20 to 1, and that's one of the space telescopes, right? When James Webb launches, the James Webb Space Telescope, that will be the most oversubscribed thing in history. But even the ground telescopes, it's sometimes 10 to 1, maybe even 5 to 1 for some of the smaller observatories that aren't necessarily considered like the biggest and the best or whatever they're still oversubscribed.
So even if you could tack little telescopes like this one on the side of Starlink satellites, the Starlink mega telescope constellation would be constantly overbooked because these small telescopes would have to focus on the same object for so long. And because it's overbooked, the rate of science discoveries that could be made on it probably wouldn't be too high. This is largely conjecture, of course, because I don't know how big of a telescope SpaceX could tack on the side of a Starlink satellite, if at all. Maybe they could put a really big one. I really don't know. But suffice it to say that I'm skeptical that this is a solution that Starlink would even want to do in the first place. And by the way, radio telescopes couldn't be tacked on the side of Starlink satellites for the same reason. Radio telescopes have to be huge, like we talked about earlier. And they also need to be far from the noise that Starlink satellites create, not right up next to it. And speaking of far from the noise, what about lunar crater radio telescopes? This is a super freaking cool idea. You launch a spacecraft to the far side of the moon, which separates before landing. One half lands in a crater, and the other half lands above the crater. The crater lander unfolds, revealing guide wires. Then the lander above the crater releases 4 rovers. The rovers drive down the crater and one by one pull the guidelines up the crater wall, raising into place a suspended secondary reflector. The rovers anchor, making this entire crater into a huge radio telescope. This is an incredibly awesome idea, and I really hope that we get to see this in our lifetimes. This would be so cool. The concept would suffer from some issues in pointing. The Arecibo telescope used to have a secondary and tertiary reflector, which could basically move around in order to point what was otherwise a stationary dish. This thing would have to have some mechanism to do so. But if they could get that to work, the listening power of it would be pretty amazing, especially because it would be on the far side of the moon, hiding behind all the radio noise that Earth makes. This is still a NASA mission concept, and it's made the rounds quite a bit, but it's probably still a few decades away, especially because of the fact that you'd need to launch an orbiter to go around the far side of the moon and relay that information back to Earth, and I don't believe we have such an orbiter today. So it's cool, and I really hope we get to see it, but I think it's probably a couple of decades off. Now here's the thing, I don't think that we shouldn't be focusing on space telescopes. Even given everything that I just said that might sound a bit skeptical. I think we need to be focusing on space telescopes way more than we're focusing on new ground-based telescopes. Especially given the fact that all of Earth's observatories are already totally oversubscribed and that the mountaintops at the best observing sites in the world are totally overcrowded with telescope domes. At the same time, we can't just wait for SpaceX and the driving down of costs in spaceflight to save astronomy. That's a straight up cop-out, not a solution. Tim said it well in the last video.
So there's this awkward overlap where, we don't have like the perfect solution for some of those problems, but at the same time, the potential for these things, in my opinion, and I would gladly be skewed otherwise, but from my opinion, the potential for good is substantially higher than the potential for harm.
Starlink has been fantastically communicative with the astronomical community, and I commend them for that, and for their commitment that, quote, they will have no material impact on discoveries in astronomy. They're setting a damn good precedent for other companies and countries to follow. And at the same time, we can't put all of our hopes into companies and countries to do the right thing. Companies and countries are not historically very good at that.
One thing that people don't think about is the fact that space law exists. The United Nations has a specific office for maintaining cooperation in space and objects in space. And so there's a reason why a country can't claim an object or an area of space as their territory, right? It's why America, when they landed on the moon, couldn't claim it as like the moon now belongs to America, right? Because of space law. And it's international space law as well, and it's upheld by the United Nations. And it's one of those things that they expect every country to sort of adhere to. But there is no space law for satellites, for how bright a satellite can be, how dim a satellite can be, how many satellites we can have around the Earth.
There's a risk that this is a new precedence and that it's now, like, okay to just kind of without any, there's no repercussions. There's no governing body that says like, this is what we can, there's no rules or guidelines really when it comes to human observations or, the value of the night sky in that sense. So therefore we don't have any way to regulate it. We don't have any way to, not even like a friendly, okay, here's our guidelines. If we could all try to stay below this, that'd really be great for everyone. Hey, nothing in the night sky that's, brighter than a magnitude 4 or something. You know what I mean? Like there's nothing like that at all, or that lasts longer than this and is blah, 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 visible for X amount of time. There's nothing like that. And I think there should be before this does get out of hand, for sure.
At what point is like the number of satellites around the Earth too much or too dense? Like it doesn't have anything like that in space law. And I find that really interesting that that's sort of maybe something that's been missed, because perhaps when space law was drawn up, international space law back sort of turn of the space race kind of era, the idea that there would be that many satellites in space was unthinkable, because satellites were the realm of, government agencies and governments, right? That was something that only they could afford, right? And it was only the commercialization of the satellite industry that allowed this sort of boom in communications and weather satellites and everything like that. The stuff that we kind of like depend on these days, right? To sort of with all our smartphones and apps that we have, right? They're all sort of running off satellite data in some way or another, right? And so it's really interesting to me to think now we look at sort of the commercialization of getting astronauts to the ISS with SpaceX and NASA saying, okay, SpaceX and Boeing, you sort out that side of things and we'll focus on maybe a lunar space base or an international lunar station, that sort of orbits the moon, and we can use that as a base to go on to Mars, right? That's sort of the sort of explanation for why NASA has sort of commercialized that launching of astronauts to space. And it's like, okay, well, we didn't foresee this outcome of commercializing satellites. So, what outcome are we going to get from commercializing, like taking humans to low Earth orbit, right? And it's one of those things to think about as well. And I love this concept of sort of space law and what is okay. If we go back to the moon and Neil Armstrong's footsteps are still on it, like, do we have there's no space law to say someone couldn't go and just rake over that, right? So do we have like a cultural responsibility to, preserve that somehow? Probably, yeah. Do we make it a museum? Like, what do we do, right?
Is this the moment to really advocate for space law about the magnitudes of satellites?
I think so, yeah. I think this would be the moment to say we need to write something into this, and there would be massive repercussions if people didn't. And I don't know who that would be necessarily policed by, if it would be the United Nations, but I think the International Astronomical Union have sort of taken on this burden as their responsibility a little bit. They are the international astronomical body though, so I guess it makes sense for them to sort of wade in and take on this responsibility. But at the end of the day, they are astronomers who are members of that society, who have their own research work to do, who are taking on that burden. This isn't someone, that they probably do have hired like admin staff and everything, but really the people with the expertise, it'll almost be like, this is your responsibility as someone who cares about this and who's a member of this society. And yeah, it's not someone who's going to be sort of like directly paid to work this out, it relies on people caring enough, I guess. So
now, a lot of this might sound like astronomers saying, hey, Starlink, hey, Amazon Kuiper, hey, Facebook's Athena, hey, OneWeb, and Russia and China and whoever else develops a satellite constellation, stop what you're doing. But that's not exactly what we're saying. We're not ignorant of the fact that access to the internet is literally life-changing for communities. Melvin John told me this about what Starlink meant for the community of the Ho tribe.
Health-wise, we're now looking at doing, telehealth or, telemental health or anything like that. And, we had a project that we were working on before we had internet down there. we're trying to get a central location for our members to do a, kind of a video chat with the doctor or anything like that, just in case, hey, maybe hurt my arm, or, does it look broken? And they would be able to make a decision there. And then you would get, moved on to the local hospital, but then I think we were probably about a month and a half in to having Starlink. And then I, just kind of like, hey, this would, this would totally fix that problem. Now we can, if we get that service, we can kind of, just give a connection to the members so they won't have to go to this one room in this one building, so then they can do it from the comfort of their own home. Yeah, especially mental health. And mental health is a big thing in our community where it's not highly discussed. I mean, especially, crying or showing emotions in the community is just like, you don't, you don't talk about it much to anybody, and, just kind of holding it in. But I think, having an outlet for someone to, talk to somebody about it, especially in their own home, would be more comfortable. So I think that would be one of them. And it kind of spun off from there as then we started thinking, there's AA groups, NA groups, with the support, family support groups, Al-Anon, all those groups, they all have online platforms. And once we started expanding that, is like, well, hey, anybody that needs to do that can do that from home. Because part of our problems is there's the bus that goes back and forth between Hoh River and Forks. But the thing is, a lot of the AA and NA meetings happen, late in the afternoon or late in the evening. The last bus is, back to Hoh River is about 5:30ish, I think, maybe 6 o'clock, and a lot of us don't start until 7, 8 o'clock. So you'd either have to find a ride home or stay the night here in Forks.
It's undeniable that Amazon Kuipers and Facebook Athenas and Starlink's service will have a huge positive impact for people around the world. Astronomers are just asking for the kind consideration of a field of research which we, the human species, have grown up with, the study of the stars. What keeps me up at night is the thought that this night sky that brought us inspiration and literally led us to the next frontier and back home to safety for millions of years could become impossibly crowded with the products of our own creation. That instead of looking up there and seeing the vastness within which we're embedded, we look up and only see ourselves, falling into the same chauvinisms and conceits that have plagued us for thousands of years. Things like thinking that we're the center of the universe, or that we're the chosen species, and so on and so forth. We are piddling, unimportant, and yet we've made it. Somehow, tenuously, just on the edge of existence, we're here, alive in the universe.